Now we're live. If Twitter's running all right. Yep, looks fine. Let's see. Can't see myself live on mobile yet, but here we go. Check sounds all right. Yep, sound is fine. Let's set a time for this 2 hours. Fill this out and then we'll get going. Almost done. Okie dokies. Right. Let's get this started. So, yes, hello, welcome everyone. Thanks for coming back. Yep, screen share working good. Pull this across. Quite like choosing the code spaces on GitHub. Actually, it's worked quite well. Hopefully, I'll be able to install Go on this, so I can do Go by example. So yeah, what I'm probably going to do is create like a Go file for each thing for like Hello World and stuff like that. So, but I need to like install it as well. Yeah, my plan tonight really is just simple. Is to just go through Go by example. I'm not gonna probably go through everything, but like, you know, go through as much as I can in 2 hours. Got a strict time limit because I don't like going over. Need to separate things, and yeah, just to bring you guys along for the ride. I think if we go through this, then there's going to be one more, what do you call it? One more sort of tutorial type thing that I want to go through, which is Go with tests, I think it's called, and that looks quite good. And then we're going to try then in the new year, like this will be kind of the end of like the Go thing for now, like in terms of like tutorials. We'll try and build something, and I think the thing that I want to build really is just want to start with a basic REST API, build a backend service, or actually connected to what I want to build for myself, which is a social media post scheduler. So maybe Go could tie into part of the system with that, if we find a good framework and whatnot to aid it. But anyway, I'm going to do Go by example. I'm going to zoom in a little bit because it's a bit small for you guys to see. I might have to think about like where I put my face in this screen and stuff like that, because you can't always see the best, but that's all right. Anyway, so we got this. We don't need that. We're going to create a new file, touch, and this one's called helloworld.go. Oops. It's not going to have Go installed, I'm just checking. Okay. So this is saying Go by example, hello world. So our first program will print the classic hello world message. Here's the full source code. So to run the program, put the code in the hello world.go and use go run. Sometimes we'll want to build our programs into binaries. We can do this using go build. We can then execute the built binary directly. Now that we can run and build Go programs, let's learn more about language. So right, okay, I've done that. So we paste that stuff into here. In fact, we'll zoom in this a little bit as well. That's way better. Yeah, I'll install that. Makes sense. I think it's going to be a bit laggy doing it through code spaces because it is through browser possibly, so like, we'll see. Yeah, so we've got that basic one. So then we do go build hello world .go, and then we list the ls, and then we can run like the binary. So go build hello world.go. What do we get? We get a hello world thing, so then we can do hello world like that. Nice. Simples. So we'll go to the next one. So okay. All commit. Hello world example. Okay. So go by examples, go by example values. Go has various variable types, including strings, integers, floats, booleans. Here are a few of the basic examples. So we've got strings, which can be added together with a plus, integers and floats, which probably behave better than JavaScript, booleans with boolean operators as you'd expect. And we can do that. So it's going to be called values. So values.go. Like that, paste that in. But one way to have it side by side. wasn't that useful. I can't. Okay, let's zoom it out a little bit. Is that still readable? Sort of readable. Yeah, that'll kind of have to be the best we can do. White's complain about that. Anyway, go run values.go. So I'll keep having to remember. So fmt.println, and then I think so variables next. So go by example variables. So I'm going to create variables.go. Not sure what it's trying to do here, but anyway, in Go, variables are explicitly declared and used by the compiler to, e.g., check type corrections of function calls. To check type correctness of function calls. Okay. So var declares one or more variables. Have that comma in between, yeah, like that. You can declare multiple variables at once. Yeah, just like we were saying then, with the comma separated. Go will infer the type of initialized variables. So if we start with the var keyword, it will infer the type. Variables declared without a corresponding initialization as zero valued. For example, the zero value for an int is 0. Okay. The colon equals syntax is shorthand for declaring and initializing a variable, e.g. For var f string apple, in this case, is just syntax is only available inside functions. So that, yeah, okay. Yeah, we already kind of knew that, really. And then go, what was it called? Variables. Okay. Constants. So we've got here, Go supports constants of character, string, boolean, and numeric values. Const declares a constant value. Okay, so it's outside of everything, outside the main function, and then here, a const statement can appear anywhere a var statement can. Okay. Constant expressions perform arithmetic with arbitrary precision. A numeric constant has no type until given one, such as by an explicit conversion. So such constants. Oh. A number can be given a type by using it in a context that requires one, such as a variable assignment or function call. For example, here math sign expects a float 64. Okay. Simple enough. Okay, next example 4. Okay, let's read it. For is goes only looping construct. Here are some basic types of for loops. The most basic type with a single condition. So while I is not is less than or equal to 3. So it's based on just a variable declared outside, okay? A classic initial condition after for loop. So initial j is 0, condition j is less than 3, and after each loop j is plus 1 each time. Another way of accomplishing the basic do this n times iteration is range over an integer. Okay, that's a nice little syntax, that, to be honest. Without the variable. So and you assign it to a range of 3, so like 1 to 3. For without a condition will loop repeatedly until you break out of the loop or return from the enclosing function. Okay, that's interesting to know you could do that. You can also continue to the next iteration of the loop. Okay, that's cool. So go run for. For example, example. We'll see some other for forms later when we look at range statements, channels, and other data structures. I like that though, and that's nice and clean. I like that. Next, if else. Okay. Branching with if and else in Go is straightforward. Here's a basic example. So you don't use the brackets really, it's just the same without the brackets. So if 7 modulo 2 is equal to 0, like no remainder, then 7 is even. If not, 7 is odd. You can have if statements without an else. Yep. Logical operators like double ampersand and double pipe are often useful in conditions. Okay. Either 7 or 8 or 7 are even. Yep, makes sense. A statement can precede condition. A statement can precede conditionals. Any variables declared in this statement are available in the current and all subsequent branches. So if num, oh, okay. Okay, so you can have a statement there and then compare it. So we say it to 9, it's less than 0, fails that. Else, if it's less than 10, it turns into that, so it's that one, and then that. Note that you don't need parentheses around conditions in Go, but the braces are required. Makes sense? And the semicolon in between it. there is no ternary if in Go, so you'll need to use a full if statement, even for basic conditions. That ain't the end of the world. So, basic switch. So, switch statements express conditionals across many branches. Classic, we know this. So here's a basic switch. So I is 2, print write 2 as something. Switch I, case, print. Okay, does this get I've not seen this before. So does this get delayed, and then this is inserted into that when it print ln is done. So I is not 1, it's 2, so it goes into that. So it says write 2 as, excuse me, oh, a bit sneezy today. You can use commas to separate multiple expressions in the same case statement. We use the optional default case in this example as well. So switch time now weekday, in case the time is Saturday or time is Sunday. It's the weekend. Default is a weekday. I quite like that. I like this time function here. That's quite good. JavaScript, that'll be a lot more pain in the neck. Switch without an expression is an alternate way to express if-else logic. Here we also show how the case expressions can be non-constants. Okay. So it just runs through the switch statement without switching on anything. It just does if-else, basically. And then a type of switch, a type switch compares types instead of values. You can use this to discover the type of an interface value. In this example, the variable t will have the type corresponding to its clause. What am I? Oh, that's interesting. Oh, so this is a function. So what am I is a function where I is an interface type, and then we switch on t, which is equal to, is assigned to I.type. And then if it's a boolean, it prints I'm a bool. If it's an int, it prints I'm an int. And if it's a don't know, it says don't know, and prints the type that is at the end. So that'd be string, I'd imagine. Yeah, don't know type string. How many have we got? We've done 1, 2, 3, 4, 5, 6, 7, 8. And there's 1, 2. Well, there's a lot. Let's just keep cracking. So we're on arrays. So it's going to be arrays. So touch arrays, go and code. So what's to say about arrays? So if in Go, an array is a numbered sequence of elements of a specific length. In typical Go code, slices are much more common. Arrays are useful in some special scenarios. Here we create an an array A that holds exactly 5 ints. The type of elements and length are both part of the array's type. By default, an array is 0 valued, which is for ints means 0. This was the thing I was remember about slices versus arrays and stuff, was that arrays being specific in their length and what type they were, and slices being a little bit more open. We can set a value at an index using the array index equals value syntax, and get a value with array index. So set a for equals 100, a, and then get the fourth one. The built-in len returns the length of the array. That's a function. Don't have to import that, it's just available. Use this syntax to declare and initialize an array in one line. You can also have the compiler count the number of elements for you with... Okay, so you spread in. If you specify the index with colon, the elements between will be zeroed. So it'll be 100, 200, 300 will be zeroed. Array types are one-dimensional, but you can compose types to build multi-dimensional data structures. So it has an array of 2, and inside that array it has 3 arrays, and they're all ints. 2D. You can create and initialize multi-dimensional arrays at once too. Yeah, so like two rows and 3 entries per row. So this one was interesting, the index. What's that come out as? It's interesting because it kind of like follows the pattern. Puts them to 0. Note that arrays appear in the form v1, v2, v3 when printed with fnt.println. Yep. Next example, slices. Oops. Slices. Go. Code. Slices are important type in Go, giving a more powerful interface to sequence than arrays. Unlike arrays, slices are typed only by the elements they contain, not the number of the elements. An uninitialized slice equals to nil and has a length of 0. To create an empty slice with a non-zero length, use the built-in make. Here we make a slice of strings of length 3, initially 0 valued. By default, a new slice's capacity is equal to its length. If we know the slice is going to grow ahead of time, it's possible to pass a capacity explicitly as an additional parameter to make. Oh, got oops. Yeah, so the slice is empty. Length is 3 and the total cap is 3. We can set and get just like oh blimey. We can get set and get just like with arrays. So that's setting, so is that, so is that, and then that one's just getting. Len returns the length of the slice as expected. In addition to these basic operations, slices support several more to make them richer than arrays. One is the built-in append, which returns a slice containing one or more new values. One that we need to accept a return value from. Append as we may get a new slice value. Okay, so it's going to be whatever S is. So A, B, C, D, E, F, and then A, B, D. Yep. Slices can also be copied. Here we create an empty slice C of the same length as S and copy into C from S. So we make it the same length as whatever S is. So S is going to be 6, I think. 6 long, and then copy C into S. So isn't that going to be C? Copy into C. Oh, copy into C from S. So that's going to be A, B, C, D, E, F, G as well. Like A, B, C, D, E, F, yeah. Slices support a slice operator with the syntax slice low to high. For example, this gets a slice of the elements S2, S3, and S4. So it's not inclusive of the number, so that's going to be B, C, and D. B, C, D. Oh wait, no, it's 0. It said arrays are 0 indexed, right? 1. So C, D, E. Right, okay. 0 indexed, okay. This slice is up to but excluding 5. So A, B, C, D, E. Yep. And this slice is up from and including S2. So that would be C, D, E, F. Yeah, okay. We can declare and initialize a variable for slice in a single line as well. Did you check the difference between the array and syntax? Okay. We can declare and initialize a variable for a slice in a single line as well. Yeah, like that. So, like a variable, but the fact that it's not given a number there is just turns it into a slice instead. Okay. DCL is going to be GHI. Yeah. And then the slices package contains a number of useful utility functions for slices. So if slices equal, so T, GHI, and T2 equal, then print T is equal to T2. Yep. That's nice. Slices can be composed into multi-dimensional data structures. The length of the inner slices can vary, unlike with multi-dimensional arrays. Yeah, okay. Note that while slices are different types than arrays, they are rendered similarly by the fmt.println. Okay. Check out this great blog post by the Go team for more details on the design implementation of slices in Go. Now that we've seen arrays and slices, we'll look at Go's other key built-in data structures and maps. Okay, so let's check this. Oops. Slices. Okay, so what's this one? So maps are Go's built-in associative data type, sometimes called hashes or dicts in another language. Dicts. I said dicts. Okay, associative array. In computer science, an associative array map symbol table or dictionary is an abstract data type that stores collection of key value pairs such that each possible key appears at most once in the collection. In mathematical terms, an associative array is a function with a finite domain. It supports lookup, remove, insert operations. Yep. Let's mention JavaScript. It's all JavaScript. Yeah, just objects in basically JavaScript. To create an empty map, use the built-in make. Make. So make map key type value type. Nice, like that. Set key value pairs using the typical name key equals value syntax. So just like objects, basically. But probably not like objects because someone's going to just correct me on that. Printing a map with eg fmt.println will show all of its key value pairs. Println map. That's nice. Yeah, nice printing. I like JavaScript, I guess. Get a value for key with name key. Yeah. If the key doesn't exist, the 0 value of the type is returned. Okay, v3. The built-in len returns the number of key value pairs when called on a map. So I'm called len2. The built-in delete removes key value pairs from a map. To remove all key value pairs from a map, use the clear built-in. The optional second return when getting a value from a map indicates that the key was present in the map. This can be used to disambiguate between missing keys and keys with 0 values like 0 or an empty string. Here we didn't need the value itself, so we ignored it with blank identifier. You can also declare and initialize a new map in the same line with this syntax. Yeah, same as like what they did for arrays, basically. The maps package contains a number of useful utility functions for maps. So make a map, and then if map is equal to n is equal to n2, then n2. Note that maps appear in the form of map key value when printed with fmt.println. Yep, simples. Functions. Okay, functions are central in Go. We'll learn about functions with a few different examples. So, Go code functions. Whoops. And then Go functions. So here a function that takes two ints and returns their sum as an int. Okay. It feels a bit weird not having the colons and stuff that I'm used to in TypeScript, but it is what it is. Not a bad thing, just interesting. And returns an int, return that. Go requires explicit returns. It won't automatically return the value of the last expression. Okay. So don't be sloppy, don't be lazy, don't assume. When you have multiple consecutive parameters of the same type, you may omit the type name for the liked type parameters up to the final parameter that declares the type. Yeah, it's just a nice little shorthand. I'm sure I'll just do it the long way though. Call a function as you'd expect with name and then the arguments. So plus 1 and 2. The result of 1 and 2 is 3, and then plus. You just give all 3. 1, 2 plus 2 plus 3 is res. What's this one? Functions. There are several other features in to-go functions. One is multiple return values, which we'll look at next. Multiple return values. Multiple return values.go code multiple. That. Go has built-in support for multiple return values. This feature is used often in idiomatic Go, for example, to return both result and error values from a function. The int in this function signature shows that the function returns two ints. Right, okay. Here we use the two different return values from the call with multiple assignment. Yeah, I like it. So 3 and 7. Here we use two different return values from the call with multiple assignment. Oh yeah, we read that, sorry. If you only want a subset of the return values, use the blank identifier. Accepting a variable number of arguments is another nice feature of Go functions. We'll look at this next. And then we hit go multiple. Whoops, go run multiple. So oh, variadic functions. That's interesting name. So touch variadic functions. Go and then go variadic. Go run variadic. So what is it? Variadic functions can be called with any number of trailing arguments. For example, fmt.println is a common variadic function. Any number of trailing elements. Here's a function that will take an arbitrary number of ints as arguments. Okay, so nums are all going to be, nums is going to be a range of ints. We don't know how many. So print nums and the blank total is equal to 0. So for blank and num in we assign these two to the range of nums. So that goes from like first value to last value. Total is we add num to the total as we loop through, and then we print the total. So we print out the whole thing, the array, or is it slice? Doesn't say. Within the function, the type of nums is equivalent to slice int. We can call len nums, iterate over it with range, etc. That's cool. So that'd be 1 and 2 and 3, 1, 2 and 3 and 6, and then variadic functions can be called in the usual way with individual arguments. If you have multiple args in a slice, apply them to a variadic function using func slice like this. Okay, so that just splits them out into like individual things. So a bit 1, 2, 3, 4, and 10. Another key aspect of functions in Go is their ability to form closures. We'll look at this next. functions. Closures. How are we doing? Long way to go. And we will stop at the timer amount because we don't want to go over. Go by example closures. So Go supports anonymous functions which can form closures. Anonymous functions are useful when you want to define a function in line without having to name it. This function, int sequential, so I guess what it means, int sec returns another function which we define anonymously in the body of int sec. The return function closes over the variable I to form a closure. So this function returns another function that returns an int, and this obviously just returns an int. So we go to main, next int, we run int sec. We call int sec assigning the result of a function to next int. The function value captures its own I value, which will be updated each time we call next int. See the effect of the closure by calling next int a few times. I think so. Touch closures. Go. Closures. Like that. So go run closures. So I imagine when we run this the first time, it's going to be a 1. It's going to +1 and return 1. Then we run it again, it's going to be 2. Run it again, it's going to be 3. New ints. So we assign new ints to int sequential. Next int. All right, okay, I see. See the effect of the closures by calling next int a few times. So that's assigned to int. Sequential is assigned to next int, and we fire that. Then when we assign it again, to confirm that the state is unique to that particular function, create and test a new one. The last feature of functions we'll look at for now is recursion. Oh boy. As we learned from one of the other streams, I am bad at recursion, so let's fix that. Okay, so Go supports recursive functions. Here's a classic example. This fact function calls itself until it reaches the base case of fact 0. So fact takes an integer and returns an integer. If n is equal to 0, then we return 1. But each time we return n times fact n minus 1. So anonymous functions can also be recursive, but this requires explicitly declaring a variable with var to store the function before it's defined. So Fibonacci, yeah. So where do you actually run the fact function? Oh, there on that line, right? So we run that. It starts with 7, and we say 7 is equal to 0. Nope. So it goes on to here. So it would be 7 times fact n minus 1, so that would be 6. So it come into here. N, and at this point 7 times the return of this. So if I change that to 3, 6. So it goes in here, starts with 3. So we do 3 times fact n minus 1. So that's going to be come in, it's not going to be 0, so it skips that, so it's going to be 2 times, I'm not sure how this works, I can't follow this. So fmt dot, I need to sort this out in my head, print ln, it's going to be n. Three, two, one. So keep storing it as it goes along, so it'll be 3 times 2 times 1. Okay. So for this case, Fibonacci, so we declare Fibonacci is a function that takes an int and returns an int. Fib is equal to, so we assign it to a function and it takes an int, returns an int. So if n is less than 2, return n, otherwise return Fibonacci n minus 1 plus n minus 2. So it starts with 7. 7 comes into here. It's not less than 2, so it goes to here. So it'll be, it returns fib. I have to draw this out one day to wrap my head around it. So it returns n minus 1, so that would be the return of Fibonacci 6 and Fibonacci 5. And then they each run, so then 5, and yeah. Yeah. Since fib was previously declared in main, Go knows which function to call with fib here. Oh boy, I don't like recursion at all. It's hard to keep track of. Add this, whoops. Go by example, range over built-in types. So range iterates over elements in a variety of built-in data structures. Let's see how to use range with some of the data structures we've already learned. Here we use range to sum the numbers in a slice. Arrays work like this too. Range, oops. Range on arrays and slices provides both the index and the value for each entry. Above, we didn't need the index, so we ignored it with the blank identifier. Sometimes we actually want the indexes though. So just print if the number is equal to 3, then it'll print index 3. So like the index is 1. Yeah. 0, 1. Okay. Range on maps iterates over key value pairs. So we create a map, and then for KV, key value in range of KVS, we print the key, the value of the key, or like I have to look up what these means. These like $S, like as a string or something maybe, and value is the second one. Printf. Okay. For K in KV, so just the keys, you can also iterate just over the keys in a map. So it'll just be A and B. Just print key A, key B. For range on strings iterates over Unicode code points. The first value is starting byte index. The first value is the starting byte index of the rune, and the second the rune itself. See strings and runes for more details. Okay, so range and go. So that's a guess. So the index is going to be 0, and the character is going to be whatever the Unicode character is. So 103 for G, 111 for O. Okay, pointers. This was a little bit difficult to understand that. Well, I understood it, but it was hard to keep track of it and whatnot. There's a lot in here. Go supports pointers, allowing you to pass references to values and records within your program. We'll show how pointers work in contrast to values with two functions, 0val and 0 pointer. I'm guessing that means .0val. 0val has an int parameter, so arguments will be passed to it by value. 0val will get a copy of ival distinct from the one in the calling function. 0 pointer in contrast, yeah, so that's a distinct like variable there on its own. 0 pointer in contrast has a asterisk int parameter, meaning that it takes an int pointer, the pointer iPointer code in the function body, then dereferences the pointer from its memory address to the current value at that address. Assigning a value to the dereference pointer changes the value at the referenced address. The AND I syntax gives the memory address of I, i.e. a pointer to I. So I in this one, so I print out, so it's going to be just 1. So 0 value is going to be 1 as 1. Well, it's going to print out 1 as well. Then the pointer, we're going to pass 1 to it, but it's going to override it with the memory address. It's going to be 0. Pointers can be printed too, so we point to that. 0val doesn't change. 0val doesn't change the I in main, but 0 pointer does because it has a reference to the memory address for that variable. characters. Strings and runes. Okay, touch strings dash and runes. And then go run strings and runes. Okay, so we got this. So go by example, strings and runes. A Go string is a read-only slice of bytes. The language in the standard library treats strings specially, as containers of text encoded in UTF-8. In other languages, strings are made of characters. In Go, the concept of a character is called a rune. It is an integer that represents a Unicode code point. This Go blog post is a good introduction for the topic. Not going to go over that now, it's too much. So const s equals, interesting. S is a string assigned a literal value representing the word hello in the Thai language. Go string literals are UTF encoded text. Since strings are equivalent to an array or a slice of bytes, this will produce the length of the raw bytes stored within. Indexing into a string produces the raw byte values at each index. This loop generates the hex values of all the bytes that constitute the code points in S. So for the length of, that's going to be 18 times. We're going to get SI. We're going to get the index of that. In F, it's going to be X. Not sure what the percentage X is. And then print a new line. Indexing to string. Yeah, I've already did that. To count how many runes are in a string, we can use the UTF-8 package. Note that the runtime of rune count in string depends on the size of the string because it has to encode each UTF-8 rune sequentially. Some Thai characters are represented by UTF-8 code points that can span multiple bytes, so the result of this count may be surprising. Rune count 6. Yeah, it doesn't look like 6, does it? A range loop handles strings specially and decodes each rune along with its offset in the string, so the index and the rune value. So we're going to print the rune value and starts at whichever index it is. Oh, excuse me. So the Unicode value of the rune value and then just the digit. And we said before that was 6, so it gets all those. We can achieve the same iteration by using UTF-8 decode rune in string function explicitly. So I and W are both set to 0. If i's length is less than s, it's going to be that. It's going to be 6. No, it was 18, wasn't it? 18. I plus equal to W. Rune value and width from UTF-8 decode runing string. So we take the string and then we get the use the index. So at this point at the start would be 0 to the end, and then we'll print starts with this the rune value and I. So rune value, not sure what it's going to be. Width equals width. Examine rune value. If the rune value equals t, else if rune is equal to this thing. This demonstrates passing a rune value into a function. Values enclosed in single quotes are rune literals. We can compare a rune value to a rune literal directly. Okay. Okay, go by example structs. So go structs are it's going to be called structs. Yeah. Let's touch. Right, so go structs are typed collections of fields. They're useful for grouping data together to form records. This person struct type has a name and age fields. New person constructs a new person with new person struct with the given name. That's a pointer, isn't it, to the struct. It's a name, and we give the P. We assign P to person. Name. Key name is name, and then we say P age is 42, and return the we return the pointer value to that person. Go is a garbage collecting language. You can safely return a pointer to a local variable. It will only be cleaned up by the garbage collector when there are no active references to it. This syntax creates a new struct. You can name the fields when initializing a struct. Omitted fields will be 0 valued, so his age will be 0. And an and prefix yields are pointed to the struct. It's idiomatic to encapsulate new structure creation in constructor functions. Access struct fields with a dot. So as we're assigning that to a person, name Sean 50, and then it's going to be a println Sean. You can also use dots with struct pointers. The pointers are automatically dereferenced. So struct pointer is equal to and s, so pointing to that, and then we'll fmt println sp age, so it's going to be 50. Sp age equals 51, and then print the sp age, which is going to be 51. If a structs are mutable, if a struct type is only used for a single value, we don't have to give it a name. If a struct type is only used for a single value, we don't have to give it a name. The value can have an anonymous struct type. This technique is commonly used for table-driven tests. Structs. Methods. Which in a while, so let's do that. Go example methods. Go supports methods defined on struct types. So we have a type rect, which have a struct width and height as an integer. This area method has a receiver type of rect. Yeah, we covered this last time. Anything. So it's given a rect. Yeah, okay, yeah. I remember now. So we point to rect type and give it a function which is called area, which returns an int, which just basically returns width times height. Methods can be defined for either pointer or value receiver types. Here's an example of value receiver. So perimeter. So that's more like a method on a class. So it just looks at like this instantiation of it. And then this is the receiver type, so perim. Here we called two methods defined to our struct. So it's going to be 2 times r so it's going to be 2 times 10's 20, 10. So perim is going to be 30. Area is going to be what was it? 10 times 5, which is 50. Go automatically handles conversion between values and pointers for method calls. You may want to use a pointer receiver type to avoid copying on method calls or to allow the method to mutate the receiving struct. So here when we assign RP to a pointer of R, so at that point it's still 10 and 5. So then the area is still RP is 10 times 5, and the perimeter is still 2 times R times 10 and 5. Yeah, I'm not too. I don't think I quite get that yet. Next, we'll look at Go's mechanism for grouping and naming related sets of methods interfaces. Oops, I didn't do the methods. Methods.go. Method. And then, whoops, and then go run methods. Interfaces, okay. How are we doing for time? Okay, we've got about half an hour left. Howdy, MZ, if you're still there. Oops. That's interesting. You still there? Yeah. Thanks for coming down. One sec, because I can't. For some reason, I can't see you on the chat thing. I can't post to the chat. What am I thinking so far? It's good. I'm liking it so far. Sorry, my chat has kind of like broken a little bit. I can't reply through the chat, but I can see what you're saying on the chat. Yeah, I mean it's good so far. I come from like a web development background, so like mainly just got JavaScript, Node, TypeScript, all that sort of stuff. Did PHP back in the day, and like a little bit of Java way long ago and stuff. This is me sort of like broadening my horizons and trying something a bit different for different purposes and stuff. But yeah, I like it so far. Like, you know, there's some parts of it there. New concepts that I don't really come across because I've not done compiled languages really before. Well, apart from a little bit of Java that I'd completely forgotten over time, to be honest. But yeah, I like some of the concepts in it and stuff. So yeah. So yeah. Do you use Go yourself? yeah, stick around, chill. Are you learning Go, or do you already know Go? I'm learning it because I want to build. I'm going to be building more products and projects and stuff, and I just want to do a completely different language for fun for the back end side of things. So you did Go for a while, but didn't stick it through. It's no props. We try things, we like it, we don't like it, or we have use for it, or we don't have use for it. I'm not going to have probably like a lot of day-to-day use for Go. This is more just me learning and just broadening my skill set and stuff. So yeah, that's fine. There's probably a delay. I'm not sure how much by. I'm still quite new to streaming stuff as well, so I'm figuring things out. I don't even have a separate monitor to see chat, so I have to keep switching back and forth from OBS to be able to see you. So yeah, but cool. Thanks for dropping by. Just come chill with us for a bit, I guess. So interfaces are named collections of method signatures. So here's a basic interface for geometric shapes. Type geometry interface. It has two methods: area, which returns a float 64, and prim, which returns a float 64. Collections of method signatures, yeah. For our example, we'll implement this interface on rect. Did I? Yeah, I put the interfaces thing in there. For example, we'll implement this interface on rect and circle types. So type rect struct width and height, type circle struct rect and height, and then we have to implement an interface in Go, we just need to implement all methods in the interface. Here we implement geometry on recs. So okay, so imagine if you did just one of them here, it would freak out if there was only like one. I'd try that actually. To complain about that? Yeah, it does. Down there. Complains on that part. Okay. The implementation for circles. All right, okay, it's just the same, yeah. So math by times by the radius and times by the radius again. That's the area. And the perimeter, 2 times math pi in the radius. Okay, if a variable has an interface type, then we call methods that are in the named interface. If a variable has an interface type, then we can call methods in the named interface. Here's a generic measure function taking advantage of this to work on any geometry. We should measure. And we pass it the geometry, so that can be anything that implements that interface. So we can print G. We can print G area, G perimeter. And then the circle and rect structs, types both implement the geometry interface, so we can use the instances of these structs as arguments to measure. Yeah. So rectangle is instantiated with that, width and a height. Circle is just instantiated with the radius, but they both have these 2 methods on it, so they can both be run. To learn more about Go's interfaces, check out this great blog post. Next is enums. So this. So enums, hope they're better than TypeScript enums. Enumerated types, enums, are a special case of sum types. An enum is a type that has a fixed number of possible values, each with a distinct name. Go doesn't have an enum type. as a distinct language feature, but enums are simple to implement using existing language idioms. So an enum type server state has an underlying type of int. Okay. Well, this is going to be enums, isn't it? Touch enums.go code enums.go. Go run enums. So the possible values for server state are defined as constants. The special keyword iota generates successive constant values automatically. In this case, 0, 1, 2, and so on. Okay. By implementing the FMT stringer interface, values of server state can be printed out or converted to strings. So we make a map from server state. This can get cumbersome if there are many possible values. In such cases, the stringer tool can be used in conjunction with Go :generate to automate the process. See this post for a longer explanation. State name map server state. State idle, state connected, state error, state retrying. Function SS server state. So it takes an int. Yeah, this is the part I don't really get this. If we have a value of type int, we cannot pass it to transition. The compiler will complain about type mismatch. This provides some degree of compile time safety for enums. It's a state idle. That's going to be 0, isn't it? Transition. It's there. Server states, it takes server state, so that should be like 0 and returns the server state. If we have a value of type int, we cannot pass it to transition. Compile, complain, blah blah blah. Transition emulates the state transition for a server. It takes the existing state and returns a new state. So if we pass it state idle, it goes to here, then it will return state connected. So this will that's fine, state idle. Stay idle. Okay. Suppose we check some predicates here to determine the next state. NS2 is transition. NS, well, that returned connected. So if we go into here, connected. A little bit weird. Not sure I follow this, but Don't normally like using enums anyway, so I think we'll come back to this. We have use cases where we can where we need to use it. So struct embedding is the next example. How far down the list are we? Got about 20 minutes left. Struct embedding, so what will we get about a quarter of the way through? There's a lot of stuff. Go supports embedding of structs and interfaces to express a more seamless composition of types. This is not to be confused with Go embed, which is a Go directive introduced in Go version 1.16 to embed files and folders into the application binary. Struct embedding. So code, oops, options I do code. Do it that way. So we have a struct called base with a number integer, and then this we add a method to it called describe, which takes the base and it just prints sprintf. Where's go sprintf? Go sprintf. Oh no, sprint t. Where is it? Sprintf. Sprintf. Sprintf formats according to a format specifier and returns the resulting string. So base with number num equals and then the value of b.number, so whatever that is, whatever we put into it. A container embeds a base. An embedding looks like a field without a name. Embedding looks like with a field without a name. Okay, yeah. So container is a type, is another struct, and it has a string and then has this as a base. So this embeds num into that, what will be referred to as base. When creating structs with literals, we have to initialize the embedding explicitly. Here, the embedded type serves as the field name. So create a variable called co, and we construct a new container. Right, so you just have to have base. Like base is the thing, base is the key. Okay, base, and then base is the struct. We have to initialize embedding explicitly. Here, the embedded type serves as the field name, and then num1. Yeah, and then string some name. Then we printf. You can access the base fields directly on co, e.g. with co.num. Okay, so I'm guessing you can't have property names that like clash and stuff. That'd be interesting. Okay. So then you print co equals num variable, and it's going to be value is going to be 1, and the string is going to be some name. Yeah. Print ln. Alternatively, we could spell out the full path using the embedded type name. Okay, so you can use either. Since container embeds base, the methods of base also become methods of a container. Here we invoke a method that was embedded from base directly in co. Yeah, so describe. Doesn't reference, it only references the number for the struct. Embedding structs with whoops. All right, yeah, that's fine. So we've got another so we've got an interface this time. The describer is one method. Embedding structs with methods may be used to bestow interface implementations onto other structs. Here we see that a container now implements the describer interface because it embeds base. Describe embeds base because of that. Okay. So code can do describer. Code describe num. Struct embedding sample. Oops. Okay, generics. How long we got left? About 15 minutes. Okay. Starting with version 1.18, Go has added support for generics, also known as type parameters. Generics. Code. Right. As an example of a generic function, slices index takes a slice of any comparable type and an element of that type and returns the index of the first occurrence of v in S, or -1 if not present. The comparable constraint means that we can compare values of this type and the double equals and the not equals operators. For a more thorough explanation of this type signature, see this blog post. Note that this function exists in the standard library as slices.index. So we have a function. Okay. So without that, it would have just been takes, right, comparable E. An example of a generic type list is a singly linked list with values of any type. Okay, so list T is any. Struct, so we have head, tail, element, and they're all just the type of any. That's a pointer to element. And type adds another struct, so element has next an element T and value, which is type of T. We can define methods on generic types just like we do on regular types, but we have to keep the type parameters in place. The type is list T, not list. So function push. Completely lost me on this one. all elements returns all the list elements as a slice. In the next example, we'll see a more idiomatic way of iterating over all elements of custom types. Crazy. Okay. All elements returns all the list elements as a slice. In the next example, we'll see a more idiomatic way of iterating over all elements of custom types. When invoking generic functions, we can often rely on type inference. Note that we don't have to specify the types of S and E when calling slices index. The compiler infers them automatically. What the comparable word means. This is type of S and B is type of E. Though we could also specify them explicitly. So slices index. A slice of strings and a string. So then LST is assigned to list with an empty where they're all integers. So head, tail, and elements are all integers, and it's just empty. So we push 10, and then we push 13, we push 23. Then we list all elements. Okay. Range over iterators. So starting with version 1.23, Go has added support for iterators, which lets us range over pretty much anything. So we have another struct. Let's look at the list type from the previous example again. In that example, we had an all elements method that returned a slice of all elements in the list. With Go iterators, we can do it better as shown below. We have a struct of like list where we have head, tail, and an array of elements that's a pointer. And then type element is, there's no comma in between that actually. Oh, tail, right, I see, right, tail is assigned to is appointed to type element as a struct. So head, tail, and tail has next and value. And these can be anything. Next is an array of that can be recursive. I don't really get that. And then value of t, so whatever that is. Function we create a variable list lst and give it, assign it to the struct pointer of that, and its method is just called push. Same things we had before, basically. All returns an iterator, which in Go is a function with a special signature. So it returns iterator.sec t list t all. So return function yield function t boolean. The iterator function takes another function as a parameter. Okay, so yield is a function that returns a boolean. As a function, takes another function as a parameter called yield by convention, but the name can be arbitrary. It will call yield for every element we want. For every element we want to iterate over, and note yields return value for a potential early termination. Yes, equal to e is not equal to nil. E is equal to e next. If there's no yield, iteration doesn't require underlying data structure and doesn't even have to be finite. Here's a function returning an iterator over Fibonacci numbers. It keeps running as long as yield keeps returning true. So the function get Fibonacci returns a iterator dot sequence return function yield. This function returns accepts a function that takes an int and returns a boolean. So it's that with a and b are both equal 1, or when not yield a, AA is equal to B and AB. Generate Fibonacci. So that sets everything to like a list with 0, pushes 10 in, pushes 13, pushes 23 in. And we do for range and list all. Since list all returns an iterator, we can use it in a regular range loop. So that's just going to print out like 10, 13, and 23. All is assigned to slices.collect list.all. So it's going to print out everything, yeah. And then for, and once the loop hits break or an early return, the yield function passed to the iterator will return false. So range over the generation Fibonacci. If n is greater than or equal to 10, it will break. Otherwise, we'll just keep doing it. Okay. That's kind of wild. Oops, I love it. Okay, next one, errors. This might be probably going to be the last one for tonight. Yeah, 5 minutes, so we'll call it that. So in Go, it's what's this one going to be called? Errors. So code errors. Go. Errors. So in Go, it's idiomatic to communicate errors via an explicit separate return value. This contrasts with the exceptions used in languages like Java and Ruby and the overloaded single/result error value, sometimes using C. Go's approach makes it easy to see which function return errors and to handle them using the same language constructs employed for other non-error tasks. See the documentation of the errors package and this blog post for additional details. By convention, errors are the last return value and have type error as a built-in interface. So function, could return an int or an error. So if the argument is 42, then it returns -1. Can't work with 42. Return -1 can't work with 42. Otherwise, return args +3 and nil. A nil errors.new constructs a basic error value with the given error message. A nil value in the error position indicates that there was no error. A sentinel error is a pre-declared variable that is used to signify a specific error condition. A sentinel error is okay. Error F can't boil water. No more tea available. Error out of tea, error out of power. So there's a function make tea, gives it an int and just returns an error. So if the argument is 2, so if it's 2, we're out of tea. Else, if the argument is 4, making tea of error power. Making tea, can't boil water. And then the number. No, can't boil water, just that. So return nil. It's never going to get to that. Well, actually, no, it's not true. Return an error or return nil, okay? We can wrap errors with higher level errors to add context. The simplest way to do this is with the %w verb in fmt.errorf. Wrapped errors create a logical chain. A wraps B, which wraps C, etc. that can be queried with functions like error.is and errors.as. It's common to use inline error check in the if line. So for a range, so that's going to go from 7 to 42. If R and E, so the result in the error assigned from F with I is the F function here. So its type's going to be 7 because it's going to be it worked, and then eventually it's going to stop. And then it's going to go to the next one. It's going to be 42, so it's going to work. This is going to do it 5 times. Errors.is checks that a given error or any error in its chain matches a specific error value. This is especially useful with wrapped or nested errors, allowing you to identify specific error types or sentinel errors in a chain of errors. So from like 1 to 5, if there is no error from make t from like 1, so make t from 1, int, so it's nope, and nope, so it just returns a nil. And the error is not equal to nil, then we do this. So if it's not equal to nil, then there is an error. So errors.is, and then we give it the error, and we check is this out of t error. Else, if error is error power, how it's dark, and then else unknown error, and the string of error string. Continue, and then regardless of what we're doing here, stuff like we say T is ready. Oh, just about to run out of time. You're going to hear my alarm go off in a sec. Get ready. 3, 2, 1. Bing bong. Go. Learning time is over. I'm going to reschedule that one. Whoops. Oh, bless me. Oh, I did a bit of sneeze tonight. That will do. Okay, so we're going to close that down. Let's go back to make sure that everything's still there. So this is where we got to. We finished errors, and then we're going to be getting to custom errors next. So what I'm going to do is I'm going to bookmark this. This is go live stream progress there, and we're going to take that one. Delete. Yeah, so that's going to be it for tonight. I'm going to call it there. Imsy, if you're still around, thanks for dropping by and chilling. Hope you got a little bit out of it, and maybe got done whatever it was you were sort of planning to get done during the stream. Yeah, thanks for coming down. We're learning Go, we're getting there. This is going to turn into a huge compilation at some point. I think I'm definitely going to look at Go with tests, because that'll be have me just like kind of doing more like implementing and stuff like that, and then we'll be looking at a simple project to build. I think we're just going to go for a backend API service and stuff to start with. Thanks for